Excellent, we're live. So Luke, do you want to introduce our speaker? Thanks very much.
Yes. Yes, today we have Professor Lei Wang. It's really a great pleasure to have him. And as I'm aware of, it's now late in the evening in Beijing. So it's very kind of him to join us for the seminar today. And he in general works on deep learning and quantum physics and computational methods. Today he will talk about differentiable programming, if I'm correct. So please go ahead, Professor Lei Wang.
Okay, so thanks a lot, Luke, for the invitation. And it's been nice to chat with everyone. So hello from Beijing. And this talk is going to be about something I really love for the past few years, differentiable programming. Let me first introduce the field I'm working on. So it's called the quantum many-body computation. So it's not quantum computation. So basically, it's a field where people study quantum mechanics problem with many particles using classical computers. And for past few decades, this field had many success, but also many more failures actually, because for many of those challenging many-body problems, we are lacking efficient algorithms. And as far as I can see, at the moment, there are two ideas, two general directions. One is on the software side, people trying to borrow ideas or techniques from machine learning, in particular deep learning. And on the hardware side, some of us were thinking about trying to use future quantum computers or even near-term quantum computers to solve this challenging problem for us. And the differentiable programming, as I'm going to present to you today, sits somewhere in the intersection of all those fields. So what is differentiable programming? It's a word recently emerged from machine learning community. So we can think it in this way. So how do we traditionally program or deal with a computer as a physicist? So usually we compose a program and give the program some inputs. The computer runs for some time and gives us output. That's traditional way where computational physicists deal with computers. And machine learning, you can view that they're doing that in a very different way. So they know the input and output and the correct output for many instances. However, they do not know how to really connect those inputs and outputs. But they just dump all those information into computer and tries to learn a piece of program. So very often this piece of computer program is going to be a so-called neural network, but sometimes it's not even neural network. But anyway, this learning procedure generates a program. Okay, that is going to be useful. That is going to solve unsolved cases for us, hopefully. So Andrew Capesi, who is the director of AI department in Tesla, he wrote this quite influential blog poster. So he was pointing out that the traditional way was this like tiny dot called software 1.0. We compose that one by line with lots of human inputs, where software 2.0 was more like specifying a search space in the program's space, and then use gradient descent to find that useful program for us. And he listed many of the benefits of software 2.0. At bottom, you see he claimed that it can be better than human, as was already proven to be true for many of the deep learning imaging and speech recognition applications and so on. So this looks a lot like rebranding of some existing technique, just like deep learning is a rebranding of old techniques from 80s. So, but I would still think in these lines of thinking, there are something that was noticing as a physicist. So let me show you one concrete example of applying those way of thinking in a physics problem. So I call this inverse Schrodinger problem. So basically, it's such a problem. So given the ground state density, how should we design a potential such that the ground state density is what we need? So let's think about this problem in one-dimensional continuous space. So we all know how to solve that. This quantum mechanics 101 problem, right? But how to solve that inverse problem? Actually, there is a differentiable programming way. So let me show you. I hope everyone can see my terminal now. This is a piece of computer program written in Python. You see that I'm pulling out PyTorch. That's a machine learning library. And you see the whole program is actually quite short, 70 lines. And I was solving this Schrodinger problem using finite difference. That's ordinary, nothing new there. And this is like, I write that solving Schrodinger equation process like a forward procedure of a neural network, okay? So input is the potential, output is the ground state wave function. And then just in the machine learning script, optimizer, we have a loss function. That is going to be the density produced by this model and the density, the target density, the difference between them. And then we have all the ingredients for machine learning, and we can just try to run that program, use machine learning library and train, so-called train that density. You see, as it runs, the density approaches to the one we wanted. And in the end, I got this quite weird potential in the gray line that is going.
Have we lost Lei Wang? Ah.
They probably updated to Big Sur too early.
Ah, that's a shame. Hopefully he can reconnect. Both of his machines seem to have gone.
I'm really sorry. I think I lost you again, right?
Yes, brief. Yeah, you are back. So we are continuing when you're ready.
This shouldn't happen. I don't know what happened to my computer this time. So it keep on restarting. I'm really sorry about that. Hope this time it will work. So just in case, let me export the PDF so I can quickly switch to another computer. Really sorry about that.
Do you want to switch to the other computer anyway?
Yes, I'm switching now
Okay.
because otherwise it's going to be. Um, okay, so let me close this one. So can you hear me now?
Yes, that's fine. Yeah.
Okay, okay. I'm really sorry for that. Let me continue again.
I think we've lost him again.
So you can all see my screen.
Yes,
right?
you're back now. Yeah. Okay, great.
Can continue. What was under the hood for that computer program? You see, I solved that inverse Schrodinger problem in use of machine learning library, and the thing, the magic at the hood is I would say the engine behind modern deep learning. Because usually when people ask a question, what is deep learning? People would usually say that they train deep neural network. But what does this sentence really mean? Deep learning composes differentiable components into a computer program, and then optimize the parameter of that program with gradient information, so that the program does what they want. Okay, and here the key technique is to compute gradient of a general computer program, and this is called automatic differentiation, because we do not want to do that manually because there are so many parameters. Okay, and I was plotting this quite complicated neural network. And let's abstract away all those complications and view that in a very simple way. And this simple view is called a computation graph. So computation graph is a way to express computation process. So you see here, there are many nodes. They represent data or parameter. And there are arrows. Those arrows indicate the dependence between data. And the forward pass, the so-called forward pass of this on the computation graph, basically it's a computer execution. And to think about the gradient, let's define something called a joint variable. That is basically the output, the so-called loss function, is gradient with respect to certain data. And by definition, you see that the gradient in the end has the adjoint in the end is 1. So the purpose of automatic differentiation is basically trying to pull back that adjoint of loss function equals to 1 information all the way through the graph until you reach all the parameter node. And this can be done locally for each node using basically chain rule. You multiply the joint to the Jacobian. That's nothing special. But this applies to more complicated computer programs, or more complicated computation graph. So for example, sometimes we have explicit or implicit dependence in the computation graph, but you just need to think locally about the process. Each node collects information from the child and gets its own adjoint and send that information back to its parents. That's it. So it's a message passing procedure on a general computation graph. And use this way, you use this approach, you can compute gradient of general computer program. And this has many advantages compared to other ways of computing gradient. For example, comparing to numerical finite difference, this is accurate to the machine precision. By the way, this is also more efficient because for finite difference, you need to perturb each dimension individually. And also there's a theoretical guarantee saying that the computational complexity of this way of doing automatic differentiation is the same as the forward path as a function evaluation. And the other thing is that since the gradient of a computer program is also a computation graph, then you can apply this idea iteratively to get the higher order gradient. Okay, and this already find many applications in science. For example, the gradient of total energy with respect to the position is force. This way you can compute the force. And also in quantum optimal control and in some quantum chemistry applications. And nowadays, with rapid development of techniques and also the rapid spreading of those ideas, people were applying that to more and more general problems. So you see here, the point is really that what was get differentiated is not a simple mathematical function. It's a rather complicated program. For example, here, Longevity dynamics is a whole molecular dynamics simulation, and here is a whole structural optimization code. And in the whole procedure, some pieces, actually most pieces were some domain-specific computations, and only a tiny piece is a neural network. You combine machine learning and scientific knowledge together into a computation graph. So it's efficient, it has the right parallel, also it's flexible. And I also want to highlight this example. That's a quite recent one from arXiv. So this was using the same technique in fusion reactor design. So you need to design all those coils parameter so it can find extremely high temperature plasma. So when you look at their computation graph, it's actually not that complicated. So the input, the parameters, the coil parameters. The output is some engineering and physics kind of cost function. But you see here, there's no neural network. It's all physical laws, right? But you can still use the same technique to backpropagate through the computation graph to get gradient, so you can optimize the whole thing. So here you see, probably you already see an opportunity of applying this to something more general than neural network, meaning deep learning. But to really differentiate a general computer program calls for a deeper understanding of the technique than simply training a neural network. So in the next couple of minutes, I want to bring to you, let's say, one or two, I think, most important things about automatic differentiation or differentiable programming. Then we are going to look into the applications in science, especially in the field that I'm familiar with. The first important fact about automatic differentiation is that there can be different so-called modes of computing gradient. Again, let's pick a simple example. It's a one-dimensional chain graph. So that's even simpler than that neural network graph. So essentially, this is a chain rule, right? Theta gives you x1, x1 gives you x2, all the way to the loss function R. And the gradient is a multiplication of a bunch of matrices. Then, as we all know that you can multiply those things in a different order to get the same answer, but the efficiency will be different. Now consider the case where loss function is a scalar, while the parameters and the intermediate results are high-dimensional vector or tensor. Then it's a good idea to multiply those things from left to the right, because this is going to be a vector. You multiply a vector to a matrix, other than starting from matrix-matrix multiplication. That's a simple fact. But this is actually, I think, one of the most used modes of automatic differentiation is called a reverse mode. It's called a reverse because this backtraces the computation graph. It's efficient for usual optimization problems with large number of parameters and a single scalar loss function. But the downside is that you need to store some intermediate result. Okay, so certainly there's another way of doing that. You just multiply these matrices from right to the left. This is called, unsurprisingly, forward mode. It's the same order. There's no storage overhead, but it's less efficient because you start with the kind of big matrices to multiply this. Usually we do not use that for optimization, but sometimes we, for high order gradient, we use that. So different ways of kind of transversing that graph, that's a so-called mode, right? This is a one-dimensional graph, but thinking about a high-dimensional, thinking about a DAG, generic graph, then there are many different ways of doing that. So the other important, I would say, perspective for automatic differentiation is actually to think them in a modular way. For example, here, I can certainly group a few steps of computation into one step, as long as I can provide it's a vector Jacobian product rule, right? So in this way, I can control the so-called granularity of the differentiation. So I can differentiate all the way down to mathematical intrinsics, right? Plus, minus, modification and so on. But I can also group many operations into higher level library calls, for example, BLAS or LAPEC matrix linear algebra calls. So in this way, there's computational efficiencies, and also this modular way of understanding, especially in the modern age, allows people to even glue classical computation graph with quantum computation graph, because quantum device is something that we never dreamed to differentiate into, because it's a physical device that's running in the lab. But as long as we had a way to run the circuit forwardly and trying to also find a way to measure the gradient like in the backward path, then we can integrate an so-called QPU, quantum processor, into the whole computation graph to think about a hybrid system. So Penny9, that's a software from Shenandoah in Canada. They pioneered in this idea. They were thinking about building up so-called like quantum machine learning libraries, so like TensorFlow, PyTorch, but for quantum processors. And this is a very hands-on example in case you really want to try it. So autograd is a nice library. Just by building up like 200 primitives, you can support automatic differentiation for almost all numpy. And I also want to emphasize that loop conditional sort, many of those control flows, they are also differentiable. So because we are thinking about some dynamical computation graph. Depending on the input or depending on the branch of the computer program, you you build up different computation graph with different topology at runtime. So now we are in a lovely world with many of the nice differentiable programming tools provided, driven strongly, I think, by machine learning development in machine learning. I recommend those lines of those tools. And with all this preparation, I think it's for us a time to talk about the differentiable scientific computing, because many of the elementary scientific operations like Fourier transform, eigensolver, SVD, they are all differentiable. Also, ordinary differential equation integration. So with that, in machine learning, people already build up differentiable ray tracer and fluid simulations. And in the field that I'm working on, I see that people are talking about building up differentiable Monte Carlo, tensor networks, DFT, molecular dynamics. So why are we doing that? That's because with the support of taking gradient, this is like a simple fact, we can more efficiently and more creatively use those tools to solve learning, control, optimization, and inverse problems. Like the one I showed to you in the very beginning, right? That inverse Schrodinger problem, solving potential given the density. So actually, in that problem, the computation graph is extremely simple. The input is that potential in one-dimensional space. I build up my Hamiltonian as a matrix, then I diagonalize it to get a ground state wave function, then I got the density difference. So the only non-trivial part is the matrix diagonalization. But as I told you, that's a differentiable. So by the way, this is a simple toy example, but behind it is also something relevant to DFT theory and DFT application, because this is relevant to something called inverse constraint problem. Okay. So what does differentiable eigensolver mean? So let's think it for a moment, because this nicely brings some connection to something I'm sure that everyone knows. So eigensolver basically is the same thing as our Schrodinger equation, right? We can view an eigensolver computationally as one step in the computation graph. So it's a branch. The input is the input node is that Hamiltonian or the matrix. The output, there are two things: the eigenvectors and eigenenergies. And we talked about the two modes of doing automatic differentiation. The forward mode was more or less asking the question like, what happens if I change the input a little bit? What happens to the downstream calculation? So this is nothing but the perturbation theory we all learned from quantum mechanics. And the reverse mode, automatic differentiation, was asking something slightly different. So again, you need to imagine that in the end, in the downstream calculation, in the end, you got certain scalar valued loss function, and for some reason, let's say you backprop that it's adjoint a few steps until you reach the adjoint of the wave function and the energy, and then locally you want to ask the question: how should I pull that information one step back to get the adjoint of my Hamiltonian? Meaning, how should I change my Hamiltonian so I can tune the loss function? So I call this inverse perturbation theory because clearly it's closely related, but it's not the same thing, because when you look into the formulas, they look like a dual version of ordinary perturbation theory. But by doing that in this way, you can use this inverse perturbation theory to solve, for example, Hamiltonian engineering problem, right? I was designing the ground state density, but you can design the, for example, the gap or the certain other properties of ground state wave function. And the other thing I talked about was a differentiable ODE, ordinary differential equation integrators. That's actually a big paper in machine learning by its own, but it's also related to many of the things in control theory. So essentially, it was saying that you can differentiate into the ODE integration efficiently without many of the memory overhead. So this gives you a way to quickly solve classical and quantum control problem. For example, in quantum control, there are actually many methods actually. I won't go into details. But if you look through the lens of differentiable programming, you are going to discover that some of the approaches are talking about forward mode, and some of the approaches are reverse mode, but with the sometimes unnecessary assumption that the control sequence is piecewise constant. So if you unify all those efforts under the hood of differentiable programming, neural ODE, I think it's a unified framework to devise flexible and efficient algorithms for quantum control. So the other thing that is probably even more related to physics is that actually many of the physical principles are related to the so-called principle of least actions. So very often we just want to minimize that action. But if you do ds, dt on both sides, you are going to see that this is also going to be related to some kind of ODE. And I was, in the keynote version, there was this animation. So basically, I think rapid descent problem is one of the most famous functional optimization problem. But if Bernoulli didn't solve that 300 years ago, now with differential programming, you can solve that. Basically, you just parameterize one-dimensional curve in a learnable way and put that into this integration. That's going to be the right-hand side of an ODE. And you just differentiate into that integration by tuning that curve. You minimize the total running time. So then let's switch to another, I would say, a field, so-called tensor networks. Talking about differentiable programming of tensor networks, that's going to be quite fun because as far as I can say, tensor networks, they, especially nowadays, plays a central role for many different efforts. Because on one hand side, they are closely related to so-called probabilistic graphic models in machine learning. So there were actually some constructive proof and many of the interesting mappings between tensor network and neural networks. Okay, and actually you might heard about that. Some people were also talking about using tensor networks for machine learning. And on the other hand, quantum circuits are special instances of tensor network. They are unitary tensor networks. And very often people use tensor network to simulate quantum circuit or to guide the design of quantum circuit. So that's why tensor network, I think, nowadays acts as a bridge. Besides that, it's actually a useful tool for statistical mechanics and quantum many-body physics. So how is going to be useful if we think about the differentiable programming of tensor networks? Let me give you a few examples. The first example is in statistical physics. So thinking about the Ising model. So there is a way to express the partition function of Ising model as an infinite tensor network. Then you can contract that tensor network into one number. This is going to be the partition function. And the way to contract a tensor network is so-called tensor renormalization group. Basically, you do cross-graining. So you shrink the size of that tensor network exponentially. But if you view this RG procedure as a computation graph, then the depth of that graph is basically the RG step. And the input of that computation process is the only parameter of the icing model, the inverse temperature. The output is a free energy, or basically partition function. And in the middle, you do some non-trivial application operations. But nevertheless, you can differentiate all the way through that graph. So you get first order gradient, second order gradient. That's going to be nothing but energy and specific heat. So basically, computing gradient gives you a way to get physical observables. So before this, usually people just do numerical finite difference to get specific heat. Because you see that many of those non-trivial steps that people do not know how to really differentiate into. So making this setup a little bit non-trivial, tensor network can also be used to solve spin glass. So that's a random, that's an icing model with random couplings. So essentially you contract tensor network to get ground state energy of certain icing spin glass. But that does not solve the problem because it only gives you the optimal energy. But you can do the same kind of gradient, right? You compare the gradient of optimal energy with respect to the field. Basically, that's the ordinary kind of response theory. Then you read out the optimal configuration. In this way, for example, you can apply that to this. You might recognize this is the so-called chimera graph instance of D-wave quantum computer. So on only one GPU, you can solve those class of instances up to 512, I think.
Sorry.
Exactly. Yeah, please.
Can I just go back to the Ising case and the specific heat?
Yes.
I mean, I would have calculated the specific heat directly from an observable using more a fluctuation dissipation argument. So,
yeah, you mean energy fluctuation, right?
Yes, the fluctuations of the energy directly.
Yeah, right. So, yeah, please.
Why is that not? Why is this more advantageous than that? I didn't quite. I mean, I just trying to calculate the energy and differentiating it, I would have thought was less reliable.
So, in this particular approach for contracting infinite tensor network, so the way people computing energy is actually to compute the, for example, so-called energy density. So basically, you had a tensor network that has a similar tensor everywhere. Okay, so that express the partition function. But then if you replace one tensor on a site, or maybe one tensor on a bound, you get the energy density. If you contract the whole thing, you get energy density. But then let's think about the energy fluctuation that involves energy square. But then this involves basically inserting so-called two impurity tensor into the network. They're going to have a different distance, different orientation, and you need to sum up infinite series and so on. So at least in this way, if we were talking about infinite lattice, it's not more convenient than simply differentiating the partition function. However, if we think about the finite case, then you're right. Like in Monte Carlo, typically people just do like that, measure total energy and total energy square. Yeah.
Okay. All right. Thank you.
This is related to infinite tensor network formalism. Measure energy square is not convenient in this particular approach.
Okay, thanks.
Yeah, okay, no problem. So let me move on to quantum problems. So this is for two-dimensional Heisenberg model and standard benchmark problem for quantum spins. So tensor networks were used as a rational ansatz for this class of problems. And a good way to optimize those tensor networks is again to computing gradient. But here you already see a bit of the spread, because you see gradient actually involves, even for this very simple problem, involves very complicated diagrams, different orientations
of the tensor where you want to take gradient and the Hamiltonian term that acts on the bound. And again, this is infinite series because we are thinking about infinite system, okay? So this complication inhibits its broader application in more challenging and complicated problems. But now with differentiable programming, you basically contract the tensor network for energy density and computing gradient, then run the optimization. So this point here represents the best variational energy for an infinite system with this approach. If you run 1 week on one GPU, let me.
Sorry, what is the system you're describing here?
It's a two-dimensional Heisenberg model.
Oh, the Heisenberg one. Okay.
Yeah. So, yeah. Sorry, it was missing from here. Yeah. So that problem has no sign problem. So that's why you have more or less exact solution from sign problem-free quantum Monte-Carlo extrapolated to thermodynamic limit. So you can do a benchmark for that point. So let me compare this with a different approach of employing machine learning techniques for this class of problem. That is using neural network to study finite size Heisenberg model on cluster. So this is the so-called neural network quantum state. So this was the accuracy obtained by Kalil and Choyer 3 years ago. So it's a bit less than 10 to the minus 3, and 10 to the minus 3 is somewhere here in this diagram. But also remember, this is already the infinite size. So these are two almost orthogonal ways of applying machine learning ideas: the neural network, the architecture, and the traditional variational Monte-Carlo optimization, and conventional tensor network, but the differentiable programming way of computing gradient and optimization. So they are orthogonal, but at the moment, I think the second approach still has lots of potential to really deliver, I think, new insight in very interesting physics. After this paper, there were some other developments for frustrated magnet, fermions, and thermodynamics, and so on. So this is differentiable programming of tensor networks. So in the remaining, I'm not sure, maybe 5 to 10 minutes, I want to then move on to quantum circuit. By the way, I also want to admit that for my own research, there was a hidden line of connections all the way connecting classical neural network to quantum circuits. So that's why, since I was talking about differentiable programming of tensor networks and training of neural network, I think it's almost it's almost obvious that talking about taking gradient on quantum circuits and talking about training quantum circuit is it's something that you can do and something maybe you can profit. So differentiable programming quantum circuit is very related to something called variational quantum algorithms. So this is a basic setup for one class of applications. So essentially, they parameterize variational ansatz using a quantum circuit. So you see that the gate parameter are the variational parameters. So this blue box prepared certain ground state, certain ansatz, certain wave function that depends on those parameters. And then you just do lots of measurement and put all those measurements to a classical computer and run a classical optimization to tune those parameters. This gives you an optimization loop. And this is so-called variational quantum eigensolver that you may use to solve quantum mechanics problem. And in the current state realization of those algorithms, typically those the number of variational parameters are small. For example, in Google, they only have one, so they just scan that parameter and looking for the minimum. In IBM experiment, they had certain, but this is again similar to the old days of variational Monte Carlo, where the variational parameters are so few, so almost some random perturbation, and some even some kind of annealing or non-gradient approach is fine. But the optimization of variational parameters in high-dimensional case certainly requires gradient information. That's a lesson actually we learned from machine learning, because they can train a neural network with millions or even billions of parameters. Gradient is actually the key, because gradient in high-dimensional space is a vector, but the function value is only one scalar. So in high-dimensional space, the information content are very different. So that literally brings us to the concept of differentiable quantum circuit. So the word differentiable here has two meanings. The first meaning is that you want to measure the gradient on a quantum circuit. And there is actually a neat way of doing that. Because certainly this is not obvious. It's not obvious at all, right? How do you get gradient information of each of the parameter, a certain quantum observable that you can measure on quantum circuit? But people work that out, and you can refer to these papers. So but I just want to point out, at the moment, this ways of obtain gradient on a quantum circuit has the same complexity as a forward mode automatic differentiation. So in that sense, it's not so efficient. But nevertheless, this is already the best people can do on an actual quantum device. So I want to spend more time talking about a second meaning of differentiable quantum circuit. This refers to computing gradient in a classical simulation of quantum circuit. Because very often, especially at the moment, we want to design or verify many of these variational quantum circuits with the help of classical machine. Straightforward idea is actually trying to implement a quantum circuit simulation with machine learning libraries like TensorFlow, PyTorch, and so on, and just use machine learning, like what I did in that tiny example, inverse Schrodinger problem, right? Just use PyTorch to take a gradient of a quantum circuit simulation for us. So certainly this works, but there is a downside. The downside is that typically when we talk about the simulation of quantum circuit, memory is a huge issue, because we need to store the wave function. So we also probably heard that in the reverse mode automatic differentiation, we need to pay memory overhead, because we need to store many of the information in the forward path, because reverse mode runs opposite with the function evaluation, right? But actually, there's a way out. This is actually quite neat. Again, let's look at the computation graph behind this kind of quantum circuit. So this is actually the same so-called comb graph as the feed-forward neural network. The input here is the quantum data, the quantum wave function, and each of this input here is a parameterized unitary circuit, and it has the same topology as the computation graph of the feed-forward neural network. But there's a crucial difference. The difference is that here, for each step, it's completely reversible, because quantum circuit is unitary. Or in a different word, quantum computing is reverse computing, right? It's reversible. But that's not true for general neural network. A general neural network, usually we cannot write backward. So this gives us a way to bypass that memory issue in reverse mode automatic differentiation, because at each step you can just do uncompute. Okay, this is the technical slide I want to skip. But the key message is that once you make use of this reversibility, you can do all in-place operation without adding caching. That actually brings to you some extremely efficient implementation of reverse mode automatic differentiation of quantum circuit. For example, here using Yao, you can train a 10,000 layer variational circuit with 300 parameters. That is something Yao is really good at. This is written by my former student and postdoc. They are leaving me now. So if you are interested, you can have a look at that. This is, I would say, some nice application of differential programming in variational quantum circuit that help us to design variational quantum algorithms. So let me stop here. I talk about the differential programming of tensor networks, quantum circuits, and more. So I think this is still a rapid developing field. I'm looking forward to discussions and creative applications from you. Yeah, thanks a lot. Yeah.
Well, thank you very much. The floor is open to questions. Anyone want to kick off?
Well, let me just ask some basic things. So can these techniques, how do these techniques work, for example, for a spin glass or understanding ground states of many body theory? I didn't understand how that works in this.
Yeah, right. So that's actually two questions and separate questions. So let me answer this one first, because this is a bit easier to explain. Actually, I omitted many of the technical details. So tensor network is a way to express ground state wave function. So basically, yes, you give a wave function certain internal structure. So then you can sandwich an Hamiltonian by two tensor networks. So you know that object is going to be a scalar as long as you contract all the internal indices. Mm-hmm. So this contraction step is the so-called forward step I was talking about, because the input for this calculation is the parameters in this tensor. That's my variational parameter. The output is one scalar value, that energy. But now the issue is how should I optimize those tensor elements? So people developed actually many ways. Okay. Some people use imaginary time evolution, or so on and so forth. But taking gradient is actually quite an obvious way of doing that. But the issue was that, especially in thermodynamic limit, that gradient is not that easy to compute. But from a differentiable programming perspective, as long as this is a computer program, there is going to be a way. But it's less kind of, it sounds that true, but it's a bit more involved than what I said. But basically, that's the idea. Yeah, that's for quantum ground state. Good. For the Ising model, that's a classical problem. That's different. Again, for partition function of a static map problem, there's a way to represent partition function as a tensor network. So here, if you contract the whole thing, you get again one number. That number is going to be the partition function. Okay. So then there is a special construction in this paper that brings the whole scheme directly to zero temperature. Meaning, if you contract a tensor network for spin glass, you get the partition function in the ground state, basically meaning the free energy in the ground state, meaning the ground state energy. But here, the issue is for really solving a spin glass, meaning for actual application, very often we want the ground state configuration in addition to the ground state energy, right?
Oh, yes, certainly, yeah.
Yeah. So in that sense, this differentiation is going to be useful. So we just differentiate through that contraction scheme. Actually, here it involves tropical algebra on a semi-ring. So it's not ordinary tensor network anymore. But again, it was expressed as a computer program. Then we compute this gradient to get the binary numbers 1, 0, 1, 1, 0 as the optimal configuration. That's a application to spin glass. Yeah.
Thank you.
Just maybe I can ask, in quantum field theory and lattice gauge theory simulations, one would often like to know maybe perhaps the microcanonical ensemble, which is it's more difficult to get information about the density of states, the entropy. Yeah, is there some advantage to this that you can see, or has somebody applied it in that context? The famous algorithms would be Wu Li or Wu Yang, I think that's called, if I remember.
Not as I know. Entropy in Monte Carlo simulation, is that some extended ensemble method like Wang Landau can be used?
Wang Landau is it? That's what I was thinking of. Yeah.
Yeah.
Wang Landau. Yeah.
Right. Yeah. But I do not see a connection with what I talk about here.
That's why I'm asking. Is there an? I would like to, if I want to compute something like that.
Let's see.
Can I adapt these techniques?
Because the entropy is not the gradient of something else. Yeah. So in Monte Carlo framework, I don't think so. But in some of the, but then I was talking about something quite different. So something along the line of these papers. So essentially, it's a variational free energy calculation, because I was talking about the variational ground state energy, but this has certainly been done, because some people also apply tensor network approach to lattice gauge theory problems, but the simple ones. In these applications, they had access to partition function directly, right? Other than Monte Carlo, where there's always a ratio. So in those applications, since they get a free energy, they get energy, they have entropy directly. Yeah. And again, this is not directly related to this. Yeah.
Okay. Other questions?
Can I ask something about the quantum circuits?
Go ahead.
Yes, please.
I have a bit of confusion here, because you want to, as I understand you, the application you have now is you simulate a quantum circuit.
Yes.
But you haven't tested yet if you have run a quantum circuit on a real device, like from IBM or something.
So the question was because it was actually yeah. Sorry for making this confusing. I talk about the two cases of getting gradient for quantum circuit, and the one I spent more time was in a simulation, because I think nowadays, especially when those circuits are noisy and they don't have good um, large enough number of qubits, very often we still need to design the variational answers with the help of classical computers. For example, how should I connect those gates? And where should I put my variational parameters? And so on. That's, for example, one purpose. Another purpose is, for example, for helping my experimental friend, because I need to run his this simulation in classical computer to ensure that this is a good variational answer, so he can reproduce it as a starting point in the lab. And for many of these applications, it's necessary to, let's say, train this quantum circuit like a classical computer program. Then here are the parameters, and then we need to compute the gradient of those parameters efficiently. And then that's the thing I talk about. And for this part, you see, it's all classical simulation of a quantum circuit.
So like soon, or not soon, if there is going to be like quantum supremacy where you can't simulate it, you can't.
No. In classical simulation of quantum circuits, we are limited by this exponential complexity. So there's no okay. We will never solve actual problem using this set of this set of simulators, because it's exactly simulating a quantum circuit, right, which is exponentially difficult. But here the purpose is to assist actual variational quantum circuit experiment. Because before they do the experiment, we need to run the simulation, probably small scale simulation, to make sure the answers make sense and to get the expected result for experimentalist. Yeah.
Okay. And then one related question is, because in real quantum circuits you have noise and stuff.
Right.
From your optimization here, from your simulation, you get some set of data, some set of parameters.
Mm-hmm.
And how are you sure they are like robust against?
Yeah, then that's a next level of issue. So here, what I'm proposing here is an ideal closed system simulation. But you see, for open quantum system or for noisy quantum circuit, there can also be a classical simulator, sometimes based on quantum trajectory or limited simulations. So in both cases, the same idea applies.
Yeah, okay, I'm familiar with. So, but you can also differentiate those approaches. That's what you said.
Right. It's going to be less straightforward than the thing I showed here, but it's the same idea, same principle. Yeah.
Okay. Yeah, thanks.
Yes.
Other question? Go ahead, Graham.
Yeah, are there any advantages to using these kind of approaches, let's say in more kind of conventional kind of DMRG type settings, or like kind of standard matrix, like variational kind of solvers, finding ground states?
DMRG.
Yeah.
Okay. I guess for one-dimensional problems, quantum problem, DMRG, I mean, the typical ones, DMRG is already the best ways of doing optimization. So this way of optimization is not going to be better. So that's also a reason why this was applied to two-dimensional cases. Because in one-dimensional, DMRG I think works most time perfectly. So in that sense, I don't think I'm not going to apply this to one-dimensional case.
Yeah, but let's say maybe in cases where you found it hard to find the specific ground state, maybe because you didn't have a gap system or something like that, or maybe you were getting stuck in some kind of local minima. Is there any potential advantage there?
No, because again, this is still a gradient-based optimization. So then there's a local minima issue applies to DMRG. Also, it applies to here. And in DMRG, they had actually even better ways of getting around this issue. I think for avoiding local minima issue, there's a different way. Again, completely unrelated to what I was talking about here. So they call it a rigorous renormalization group. Essentially, it's guaranteed algorithms that works for gapped one-dimensional system. So that actually has no issue related to local minimum. So that's one comment. So the other comment is for local minimum, I think in general, I think there's no general solution, right? Because optimization of higher dimensional problem in general is NP hard. So, but from a physics perspective, very often good initialization really help. And as far as I can see, recently there's some new progress in along this line. For example, some people find a way to map many of the so-called pattern wave function. So basically, Kurzweiler project wave functions that was usually used in Variational color into MPS. Then use this to initialize DMRG calculation, hoping that it get around this local minima issue because it's already some sensible starting point. Again, in this case, it's unrelated to what I was talking about here. But you see, I'm sorry that probably I conveyed this information that differential programming is is a kind of a super useful. No, it's not. It's a useful if you use it in the right place. Yeah. Thanks.
Thank you.
Other questions? I have one last question. If I heard you correctly, you mentioned Hamiltonians with a sign problem, and
Yes.
you stuck to the case where there wasn't a sign problem, but it was the implication that there was some advantage to this in cases with a sign problem that has been found?
Right. Yeah. For example.
Or can you comment on that?
Yeah. Okay. So there was one application along this line, basically applying that to J1, J2 model that has a sign problem. Again, this is a typical problem that people wanted to study with this class of technique, the tensor networks. So advantage, I mean, compared to Monte Carlo, there is let's say quantum Monte Carlo is not useful there because there is a sample. Then the typical technique people used for those class of problem was a variational Monte Carlo. Okay, usually with very few parameters. Sometimes with a lot of parameters, meaning a neural network. Okay, and the roadmap along what I was talking about here is with differential programming of tensor networks for this problem. And then compared to Variational Monte Carlo, as far as I can see, the advantage is that it's a family of easier to optimize rational answers for the following reason. In variational Monte Carlo, they also use gradient, by the way. The gradient are noisy because they get sampled from Monte Carlo sampling. But in tensor network calculation, the gradient is deterministic because the construction is a deterministic algorithm, even though it's an approximated gradient. But from the optimization perspective, with a deterministic gradient, some of the higher order technique applies. For example, we can easily use Cauchy-Newton, but in variational Monte Carlo, the efficiency is an issue. Yeah. So that's why, from this perspective, I believe it's not a very strong belief, but I do believe that along this line, there is a hope to produce useful new physics for frustrated magnet and other problems like fermions, where there is a sign problem. Yeah.
But the difficulty there, and the difficulty with those systems with a sign problem, is that the case without a sign may not be the dominant configuration, because the sign can cancel what you think is the dominant configuration. You get interference.
Yeah, right. Yeah.
So I'm not quite sure why this would help.
Oh, okay. Because maybe I missed your question. I was really talking about it in a different way. Yeah. So because the thing I explained was I was trying to telling you the advantage of using tensor networks compared to variational Monte Carlo. Yeah. But I guess your question is more related to whether this can help us to solve sign problem, right? To directly address sign problem. Is that correct?
I mean, that's the real issue in when you're in a system with a sign problem. What you normally do is you try and do some reweighting if the sign problem is not serious.
Yeah. So,
but that's only the very special cases.
No, I got your point. So
to see if one could get for.
Yeah. I don't have much to say, but let me point it out. Actually, there were already a few papers of applying this idea to quantum Monte Carlo, where you want to we know that average sign in Monte Carlo simulation is the basis dependent, right? So you can do local basis transformation to change, reduce. Okay. Another fact is that to measure average sign in quantum Monte Carlo simulation has no sign problem. You can always measure your average sign, right? Because you never divide anything in the estimator. So then here comes the idea. Basically, they just parameterize a family, actually sometimes a big family of different local unitaries as a basis transformation. Or in some other algorithms, that's related to correlated fermion, because they have to use Hubbard-Stratonovich transformation to decouple the fermionic interaction. But there are certain degrees of freedoms in such a decomposition, because you can decompose into different channels. And also, this channel can have a spatial dependence. So there are huge space in the quantum Monte Carlo algorithms design that people did not explore, actually. Because usually, especially in my field, usually for Hubbard model, people decompose to spin channel. For some other problem, for particular reason, they decouple to hopping channel. But if you just make the whole thing flexible and trying to optimize average sign measured in a Monte Carlo simulation, there's a chance that you'll find the right algorithmic configuration to maximize your average sign. And we all know that the improvements from the increase of the average sign can be exponentially helpful, because it reduces lots of sample in the next round of simulation. So there are some efforts, but I will never claim that there's an advantage. I will never claim it's going to help us to solve this. I don't think it's going to solve sample. It's more like kind of a elevated sign problem in a particular application. Yeah, I'm not sure I addressed.
Okay, thank you. That's that. Yeah.
Okay.
Other questions? Perhaps I will stop the recording and we can go to a less formal setting. Okay. All right. Thanks again to Lei Wang for your talk. Okay. It's a rather silent format.